Hi. I'm Kevin from NCD Group. Today, we're going to take a look at how the final tab of our simulator works, the Space Mission Planning tab. Well, to be fair, this isn't actually the last tab in the simulator. There's still the About Us tab. But it's not particularly interesting since it mostly deals with the EULA conditions for using the software platform. The most important points to highlight there are: an internet connection is required for both installation and API functionality. One license can be used on multiple devices as long as they belong to the same user. But licenses cannot be transferred or shared online. It also mentions that the system tracks 173 celestial objects. Back to the simulator itself, the first thing we would do in this tab is print the documentation labeled Preliminary Concepts. This section provides a detailed explanation in terms of conservation of angular momentum and mechanical energy of the different types of orbits a spacecraft can achieve depending on its velocity, as well as the flight duration based on its trajectory. It goes in depth on all three types of orbits, includes calculations for eccentricity, relative angles between the two planets required for a rendezvous, and so on. It also introduces concepts such as Hill spheres and the heliocentric, or actual, velocities of the spacecraft within the heliocentric system, factoring in planetary drags. The physics may be a bit dense for those not familiar with the subject, but it's very well explained. Towards the end of the PDF, you will find detailed examples of how everything works, as well as methods to verify the accuracy of the data. The final pages explain how fuel calculations were performed. Back in the simulator, we move on to selecting the objects involved in the space mission we want to plan. The origin doesn't have to be Earth. Theoretical objects are allowed as well. In the example, we simulate a launch from Venus to Jupiter on a selected date. We increase the simulation speed by 10x to avoid delays. Choose the type of trajectory based on the escape velocity multiple, and input the payload mass, assuming zero mass for the spacecraft. We click the Simulate button and view the orbit from a heliocentric perspective to observe the rendezvous. The simulator calculates data such as the next 5 available launch windows. When possible, note that the built-in API data only goes up to the year 2100, which may be limiting for Neptune-bound missions at low velocity. It also shows the error margin, the arrival date of the spacecraft at its destination, the next alignment date at the destination for a possible return to the origin planet, and the return to the origin planet, displayed in the Return to Earth column. The simulator also provides us with the advance, positive angle, or delay required for the destination planet to enable a rendezvous, the angular displacement of both origin and destination planets during the spacecraft's flight, the orbiting speeds, A and B, of the origin and destination planets, the launch velocity v1, the insertion velocity v2 for entering the destination orbit, the total flight time, the required fuel mass, the orbital eccentricity, the flight distance in astronomical units, as well as the actual delta V applied to the spacecraft for orbit injection and descent to the destination, and the total kinetic energy needed. We assume the spacecraft is single stage. All of this data can also be printed by clicking the Print Results button at the bottom. Finally, the tab includes a mini-game where you simulate a launch from Earth to Mars. The goal is to press the button when you think the launch window is optimal based on Mars' relative advance as it traces an elliptical orbit. If you succeed, you then have to prepare the return launch from Mars to Earth. Thank you for your attention, and happy space exploring!
our content, hit like and subscribe to the